All right, if you're in computer science, you live in this really cool, perfect world of logic, right? A 1 is a 1, a 0 is a 0. It's all clean, abstract, digital. But underneath all that elegant code, there's a messy physical reality. And today, we're going to pull back the curtain on a hidden flaw, a little ghost in the machine that's in every single chip ever made. You know, we all learn that a transistor is the absolute foundation of computing. It's just a switch. Give it some juice, it turns on. Take it away, it turns off. And it happens instantly. That's the basis for every single binary decision. But what if that core assumption we all rely on is just plain wrong? So this is the ideal world, right? Straight out of the textbooks. A transistor in saturation, that's a closed switch, that's your 1. In cutoff, it's an open switch, your 0. It's a perfect, clean binary system. Super simple and just beautifully logical. Logically, it follows that the jump between these two states, from off to on, from a 0 to a 1, should take 0 time. It ought to be a perfectly vertical line on a graph. I mean, that's the bedrock of digital logic. And here's the glitch in the matrix. This quote right here spills the beans. The transistor can't turn on suddenly. It actually takes time. And the culprit, the reason for this annoying delay, is something called internal capacitance. So what in the world is capacitance? Well, in the simplest terms, it's just the ability to store an electric charge. The best way to think about it is like a teeny tiny invisible battery inside the component. Every time it needs to switch on, it has to charge this little battery up first. And every time it switches off, it has to drain it. And that process, it's definitely not instant. That's the real head scratcher, isn't it? If you look at a diagram of a transistor, you won't see a part labeled capacitor. So where is this phantom component hiding? Well, to find it, we've got to go deeper into the physics of the semiconductor itself. The answer is right there at the heart of the transistor, the p-n junction. This is just the spot where two different types of semiconductor material meet up. You've got p-type material, which has a bunch of positive charge carriers called holes, and then you've got n-type material, which is swimming in free electrons. So what happens when you stick these two materials together? Well, the free electrons from the n side immediately rush over to fill in the holes on the p side. This creates this little neutral zone right at the junction where there are no free charge carriers left. It's been depleted. And we call this the depletion region. Okay, now here's the crucial part. Look at what we've just created. We have a conductive layer, the n-type material, another conductive layer, the p-type material, and smashed right between them is an insulating layer, that depletion region. A conductor, an insulator, and another conductor. What does that sound like? Yep, that is the exact physical structure of a capacitor. It's not something we added, it's just a fundamental property of the physics. And this built-in, totally unavoidable capacitor, it comes with a price. It basically creates a physical speed limit on how fast we can compute things, and every single switch pays that price. Just look at this. On the left, that's the dream, the perfect square wave you see in your CS classes. Instant on, instant off. But on the right, that's the messy reality. The signal doesn't just snap on, it kind of curves its way up. It doesn't snap off, it slopes down. That curve, that delay, that's the time it's taking to charge and discharge that pesky internal capacitor. Now, engineers have actually broken this delay down into 4 very specific parts. First, there's the delay time, just to get things moving. Then you have the rise time for the current to get from 10% up to 90%. After that, there's a storage time where extra charge has to get cleared out of the way. And finally, the fall time for the current to drop back down. All of those tiny bits of time add up. So to boil it all down, the very same physics that makes a transistor work also creates this unwanted or parasitic capacitor. And this thing fights every single change of state, costing precious time. We're talking picoseconds. This is the hidden flaw, the fundamental bottleneck that puts a hard limit on your CPU's clock speed. But what if this flaw wasn't really a flaw? What if some incredibly clever engineers looked at this so-called problem and thought, hey, maybe we can use this? This is where the story gets really, really good. So check out the MOSFET. This is the kind of transistor in pretty much every modern CPU. Here, engineers did something just brilliant. They intentionally stuck a super thin, high-quality insulator, silicon dioxide, right in the middle of the device. They didn't try to get rid of the capacitor. They leaned in and actually perfected it. They turned the bug into a core feature of the design. So why would they do that? because by controlling this capacitance, you can do some amazing things. This effect is absolutely essential for the cells in your computer's DRAM that store memory, for the pixels in your phone's camera sensor, for tons of other electronic components. The flaw became a powerful, controllable tool. And that kind of leaves us with a final thought. The perfect abstract world of computer science is only possible because engineers learned how to understand, predict, and even exploit the messy, imperfect world of real-world physics. It really makes you wonder, what other bugs are just sitting out there waiting for someone to turn them into the next revolutionary feature?